Greetings and welcome to the video on point and interval estimates. Let me just take a quick opportunity here to get this up on the board for us. So point and interval estimates. Okay, let me just start with the first one. Let's just start with a point estimate. So point estimate. Let's just talk about what the definition of a point estimate is. Well, essentially, in just written form here, and then we'll give a little bit more of an example here. It's just a point or a value. In our case, it's going to be a value. It's going to be the mean or the x bar. It's a value that is used to estimate a parameter. So let's go back over what a parameter is just briefly. If you remember, this is on one of the earlier videos where you'll have a statistic. In this case, the statistic will be our value that we were talking about up here, the statistic. And then you'll have parameters. Statistics are things like, our x bar, our s squared, which was our variance, our s, which is our standard deviation. And the x bar is an estimate of mu, if you remember. So this is the statistic notation is x bar, the parameter notation is for the population, and that's mu. S squared corresponds to sigma squared, and S corresponded to sigma. So these were the sample statistics here, based on samples again, and these are the parameters the equivalent parameters based upon known population values. Well, these are oftentimes, most of the time, unknown for us, right? I mean, if the population mean and standard deviation was known for your intervention, you wouldn't have to do the study, right? So what you do is you don't know these values, so you sample your relevant population, you perform your intervention, you find out what the differences between the means are, and then you want to infer those back to the population. Okay, so we don't know these, but we know that this x bar is actually going to be used to estimate a parameter, and the notation for this that we use is the following: that the point estimate, and in this case, is x bar. So the point estimate of the sample mean, remember this here is the sample mean, equals mu. So the point estimate of the sample mean will be or equal to mu, which is the population mean. And this basically denotes that the sample statistic, the x bar, is an unbiased point estimate of the parameter of mu. Now, what allows us to kind of say this? Well, there's a law here called the law of large numbers. I won't go into this in detail, but the law of this will be intuitive, numbers. The law of large numbers essentially states that if you take any kind of value, in this case the mean, of a certain sample size n, it will converge. Read this one here. Read this as converges to. So a mean of any size n will converge to mu with probability 1, 100% of the time is what that means, as n, read this arrow as approaches infinity. Read this as approaches. Okay, so let's just kind of unpack this just for a minute. What does this mean? probably the best way to do this is if you've seen me kind of do this before, but if you had this kind of pot, I call this a pot of beans here, and this was the population pot of beans of a certain size n here, and from that you pulled some beans and you put those beans into a smaller little bowl here, and this is your sample little n, right? And let's just say right now that this represents a sample size of n equals 5 beans here, jelly beans. Call these jelly beans, that's fine. So this is a population of all jelly beans. You don't know what the average of all jelly beans are that are being produced in the United States of America. And it's a silly example, but let's go with it. So what you do is you draw a sample of n equals 5, and you get maybe a mass jelly beans of something, I don't know, maybe 2.2 grams. Okay. Now, the question I would pose to you is this sample mean? Let me try to actually write in here. This x bar equals 2.2 grams based on this n equals 5. Let me put a box around this in blue. Would you expect this sample mean to be the exact mu over here? And the answer is no, right? You know that there's sampling error, that every single one of these 5 beans that you pulled out is not going to be exactly what the population mean is. And so the point here is that the law of large numbers states that if I went from a sample size of a little sample pot of beans of n equals 5 to something larger, that maybe this is now n equals 5, that, I'm sorry, not n equals 5, n equals 10, I'm going to make it larger. If this went to n equals 10, that whatever this value is, whatever this x bar was, this x bar here would be closer or start to approach mu. It'd be a better estimate of mu because it's based on a larger amount of beans, right? If I did this again, and now my pot gets even bigger, and I'm doing this now on n equals 50 beans, that this x bar, let's say that this one's of 10, that this x bar, which is based on 50, would even be a better, would even converge closer to mu, or the population mean. And hopefully intuitively that makes sense to you, that the law of large numbers says that as n approaches infinity, as you get a bit larger and larger and larger sample size, your sample mean is going to come closer to what the population mean is. That's just another way of saying that. Okay, so that's the concept of a point estimate. Okay, so let me just kind of section this off here. Let's talk about what an interval estimate is then. Just again, we're introducing these concepts at a very high level here. The interval estimate says essentially that you have a range or band, I'll put this in parentheses, or band if you want to think of it that way, around the point estimate. And the parameter is presumed to lie in the band. Caveat: with some level of certainty. Okay, so what does this mean? An interval estimate, it's really building on the concept of the point estimate, and it makes sense that going back over here to this this n equals 5 example, let me just draw you into where I'm talking about here. So I'm back over here. Okay, if we know that the point estimate from the sample mean of 2.2 grams, we know that it won't exactly be what the population mu value is. But it is reasonable to assume that one of the values that mu could actually be is 2.2 grams. But it could also take on some other values, and we can put an interval or a band around that point estimate. So for example, let me just say down here, and we'll just kind of draw this example out. So if the average mass of jelly beans in your sample is let's say this is x based on the 5, again, is 2.2 grams. We could put, I'm not going to tell you how yet, this will be after we have to build on this concept a little bit more, but we can put an interval around this. And so it could be that your interval looks something like this, that maybe, I'll put this in brackets, that maybe your interval around this was 1.2 grams to 3.2 grams, and that was your interval estimate around this point estimate over here. So let me bracket this in a different color. So this is the interval estimate, and this interval estimate is around this point estimate. In other words, this point estimate here would lie exactly in the arithmetic middle of this interval here. Okay, so let's just say maybe you think that's a rather large interval, you know, plus or minus 1 gram. That might be that's a lot of mass to vary really in something that weighs so little. And so maybe you say, well, let's draw this down a little bit smaller. Maybe if you did the if you based this x bar instead of on 5, maybe you did it on 10 and you still got 2.2 grams, that maybe the interval around it was 1.7 grams to 2.7 grams. You would say, okay, even though I got the same middle point right here of 2.2 grams, my overall width of this, the width of this here, is narrower, right? My point estimate had more precision to it, because or I should say my point estimate was still the same, but my interval estimate has more precision to it. Why? Because my sample size went up. Let's just say you did the sample size again. This time it was on the n of 50, and you got still 2.2 grams for your point estimate, but now your interval goes from maybe 2.1 grams to 2.3 grams. So plus or minus 1/10 of a gram. You would say, again, I got the same point estimate here of 2.2 grams, but now that it was based on 50, so let's just say this one was based on n equals 5, this one was n equals 10, this one's on n equals 50. So what you saw is as sample size increased, the width of my actual interval decreases, right? And that makes a lot of sense, that as you gather more and more data, you're going to be more and more precise on how you can estimate what the actual mu value would be, or the actual population value would be. And so this introduces to us the concept, again, at a very high level, of what a point and an interval estimate is. We need to build on this now, because to really grasp this, we need to understand a really fundamentally important concept of inferential statistics. And remember, we're leaving descriptive statistics behind, we're moving to inferential statistics, and that is really the concept of a sampling distribution. And so the next video is really going to build on that concept. So I hope you enjoyed this video. I hope it's clear. I hope we didn't muddy any water. And let's check out the video on sampling distribution.